Hi, in this video we'll see the simulation of MOSFET devices. So we'll see the IV characteristics MOSFET. So we know MOSFET can be represented using this symbol. So it will be having four terminals actually. So this is gate, drain, source. If I write it like this, then this is a NMOS FET and this is the bulk. And we can apply voltages over here, one power supply and other power supply will be connected here. This is the ground. I'll say this as V1, V2 and this bulk is usually connected to source, and we will have V1 voltage as equal to gate to source voltage and V2 as equal to drain to source voltage. And we want to see the characteristics of this. Before we see the characteristics of this, we shall see what are the parameters of this MOSFET in a typical model file. Because if I want to know the IV characteristics of this, for a simulator it should understand this is a MOSFET having certain parameters. Suppose if you look into the cross-section view or the 3D view of the MOSFET, it looks like this. If you consider this as bulk, this is source, drain, and you have the gate oxide. This is gate. Assume that this is gate, and if it is a NMOS transistor, this is P minus, this will be N plus, this will be N plus, and if I say this as source, this as drain, if you write its 3D view, it looks something like this. This is how it looking. Now we can just write it this way. It may not be a very good picture, but still fine. This is how it looks, and this happens to be the length of the transistor, and this is the width of the transistor. And coming to other specifications of the MOSFET, so it will going to have mu n Cox, where mu n is the mobility, Cox is the oxide capacitance, and we will also have threshold voltage VTO. So these are the important parameters we need to specify. Of course, this is also written as Kp, kappa of the transistor. Now typically we will take the value of Kp as 200 micro ampere per volt square, and VTO can be 0.4 volt. These are the typical values. Now of course the width and the length of the transistor will be at the user discretion. He can able to take any values. So usually it will be in terms of either nanometers or micrometers. Now let us try to realize this particular MOSFET characteristics there. And of course we know the expression for the drain current both in linear and saturation region and also in the cutoff region. So when VGS is less than VTH, of course this VTO is nothing but VTH only, threshold voltage. If it is this, irrespective of the value of VDS, MOSFET is in off condition. So MOSFET is off. When it is off, I know that ID is equal to 0. This is under typical conditions. Suppose if VGS, this is less than or equal to, for transistor to turn on, VGS has to be greater than VTH. Suppose if this drain to source voltage, if it is less than or equal to VDS SAT, where VDS SAT is given by VGS minus VTH. If this VDS is less than VDS SAT, I will say MOSFET is in linear region. This is in linear region. For that, expression would be ID in linear is equal to half Kp W by L. It's 2 VGS minus VTO into VDS minus it is VDS square. Okay, this is the expression for the current. Now we will see, of course, for this to happen, the MOSFET should have a VGS greater than VTH, but VDS should be less than VDS at. So there is other possibility where the MOSFET, this is greater than VTH and VDS is also greater than VDS SAT. In such case, the ID expression will be, of course we call it as MOSFET will be in saturation region. Saturation region, for which ID SAT expression will be half Kp W by L VGS minus VTO whole square. Of course, we interchangeably write VTO and VTH, so both are same. So this is the expression. If the MOSFET is in saturation, you can say it is independent of VDS. There is no VDS term here, but here it depends on VDS. So let us try to verify for different values of VGS, Kp, WL and VTO, the MOSFET currents. Okay, let us try to get these values verified. So let me, okay, we will be using LT SPICE, which is linear technology. SPICE stands for simulation programming with integrated circuit emphasis. So let me just type it here. Suppose if I just see what is SPICE is. This SPICE is nothing but simulation program with integrated circuit emphasis. Okay, this is S and this is P. Oh, let me just make this as black. A. This is now black, and this is again it is, this is SPICE. This is C. I am just specifically saying this is because you should know what is SPICE is. Simulation program with integrated circuit emphasis. So we have this LT SPICE. This is LT SPICE of any version you can take. Let us start using this LT SPICE to understand the working of MOSFET. Now I have this window where I can start drawing the circuit diagram. Since I want to have the MOSFET which is something like this. Now this need to be rigged up. So let us do the same thing. So I will have the components, because if you see this, what you want here is, so let me just take this also. Where is that? Okay, it's here. Let me just put them side by side. I want to make it one-to-one. This is my MOSFET. MOSFETs are available here. So this is component. You can click on this. You will get various components available, out of which I am looking for a NMOS transistor. You can see there is a NMOS 4. NMOS 4 is one which is something like this. Now you can see this is NMOS. Uh, Suppose if you are taking one more NMOS, this assume that if you take one more NMOS, again go here and then take one more NMOS, it will be, you can see M1, M2. This is how it will get updated by itself. So it will be incremented by itself. Since I don't want to have two MOSFETs, I want to take out this, I want to delete this. For deleting, you have this option, cut. That is scissor. Take this and then cut this. Now what I have is, let me just verify. Okay, it's fine. Now I have to use these two sources, V1, V2, and then ground, and of course I have to make the connections. So sources are again here in the component. Because it is one of the component, I'll go here and look for voltage source. So this is my, you can see here, it's a voltage source. It can give either DC, AC, pulse, sine, PW, pulse width variation, exponential, and you can have different specific type of sources. Now since I want to have a DC, for any such sources you can use this. So I'll use this voltage source. One is at the gate, other is at the other point over here. Now since we name it as V1, V2, it is so V1, V2. So now I have to make the connection. So connections, you have to use this wire. So you can see now I have selected this. Let me click on this, again click. Now this is the destination. You start from here and then you can see I'm stopping here. Again you just make this connection. Of course once you get used to it, it looks very easy. Maybe first few classes you'll slightly find it new, otherwise it is fine. You can see now I can get a ground here because this is my ground. So ground here, you can take this as your ground. This is ground. Let me make that connection also. Now over here in this we have mentioned V1 is VGS and V2 is VGS, and we have just considered different conditions, and we also said that there are two process parameters for this MOSFET to define. So this I had to do before I just assigning some voltages and do the simulation. Now for doing that, you can see there is a .op spice directives, because for the simulator I should say what are the specifications of this. So as I said here, so over here I have written it as KP and WL as so on, sorry, VTO as this much, and of course I need to specify what is the width of the transistor, what is the length of the transistor. So these are usually same for all the MOSFETs, whereas this W and L, which is length and width of the transistor, can vary if you have more than one transistor, whereas this KP and VTO will be same for all the transistors, meaning if you have more than one transistor, there should be one parameter which is defining, there should be one file which is defining all these process parameters, whereas individual MOSFETs you can edit the value of width and length. So that's what is the entire idea. So let us come here. So as I said, I need to give KP and WL, that I'll give it here. So go to the spice directives, and here I need to type of course I'll just type it and show you where the syntax of this is available. So it is dot model, give a space, say it as NMOS, say it as one more NMOS, open the parenthesis, close the parenthesis. Within the parenthesis you write KP equal to 200 U, that is 200 micro. Because there is no mu possible, simply type it as U, small u, or capital U, doesn't matter. And VTO, put a comma there, VTO is equal to 0.4. So these are the two parameters that you specified for the model, where KP is 200U and VTO is 0.4. So this is now the representation of this particular MOSFET, which we thought, okay, this should have KP and this VTO is this. And of course we are not yet defined width and length. So let us go back here and then define what is width and length here. I will just come here. So let me specify width as 10 micro and sorry, length as 10 micro and width as 500 micro, so that WL becomes 50. WL becomes 50. Now we have defined the process parameters as Kp is 200. Kp is nothing but mu n into Cox. VTO is 0.4. I have defined the dimensions of this MOSFET as 100 micro is the length, 500 micro is the width of the transistor. Now let me specify this voltage. This is the voltage name, this is the voltage value. So let me give it as 0.2 volts, 0.2 volts. And let me give any voltage. It can be 1 volt, 2 volt, or it can be 0.4 volts. Now since I applied a voltage less than VTH or VTO, the MOSFET should be in cutoff condition as per our knowledge. So as we have studied in the class, VTO, if VGS is less than VTH, or even if it is equal to, the MOSFET is in off condition, so it should be, ID should be 0. So let us see what is, because this is your VGS which is less than VTH of 0.4, so MOSFET should be off. Suppose if I, now this is the option for running. If you say run, it will ask for what simulation I have to do. Since I'm looking at only the current and voltages, I will opt for DC operating point. This is my DC operating point. You can see here it describes compute the DC operating point treating capacitances as open circuit and inductances as short circuit. Meaning, if at all, if you have any inductor capacitor in this particular circuit, for any circuit, if you do this dot OP, that is what is this dot OP, it will consider all capacitors as open circuit and inductors as short circuit. Since we don't have anything, nothing to worry about there. Suppose when I say dot OP, you can see dot OP came here. You can see immediately I got all voltages and currents of this particular network, of this circuit. You can see it is 1, that is this one. Can you see this is 0.2, this is 0.2. Can you see now here ID of M1, this is M1, ID is drain current. Can you see it is 2.01 picoamperes. Actually what I said was the current is 0. The current is 0. This is in the ideal case, but typically it will be very small current. Now this picoampere is negligibly small, so we treat the MOSFET as in off condition. Meaning to say, when the MOSFET is having a VGS less than VTH, the MOSFET is off. Now let us make the VGS slightly more. So let me make VGS as 0.6. 0.6. Since it is 0.6 and VDS is 1 volt, in which region the MOSFET is operating now? Suppose this is VGS. What is VDS SAT? We know that VDS SAT. Okay, let me just go back here and then show you. Suppose if VGS is 0.6 and VDS is 1 volt, for this what will be VDS SAT? VDS SAT, I know that it is VGS minus VTO. VTO is 0.4 here. This is 0.6 minus 0.4. This is 0.2. So VDS SAT is 200 millivolts. But how much is the VDS you actually have? You have 1 volt as the applied VDS. So now, therefore, the condition is VDS is greater than VDS SAT. So this was the condition for keeping the MOSFET in saturation condition. VGS is more than VTH. VDS is also more than VDS SAT. So MOSFET should be in saturation. So I have to get a current ID is equal to half Kp W by L VGS minus VTO whole square. So to be very frank, I should get this is half into 200 micro into 50 into 0.2 whole square. This is the current what I'm expecting. Just give me a minute. I'll calculate and then let you know. Okay, now we should just do the calculation. Now it is 0.5 into 200 micro into 50 into 0.2 whole square. So I should get a current of 200 microampere. So ID expected is 200 microampere. Let us see how much we are getting. Suppose with this as 0.6, this as 1 volt. If I run, you can see I'm getting a current of 0.002. Of course, you can see here 0.0002 is actually 200 microampere. So this is actually 200 microampere current. So this is to show that whenever we have a circuit which is of something like this, so this is the circuit. I made it 0. First we made it as 0.2 and this was 1 volt. We found that MOSFET was in cutoff region. Then we just made it 0.6 with a VTH as 0.4. It is more than 0.4 0.4 volt, so MOSFET is on. Now with this as 1 volt, MOSFET is in saturation. Then we use this equation, got the current as 200 microampere, it is coming. Now let us consider this condition where VDS is less than VTH, that is it's less than 200 microampere, because we know that VDS sat is 0.2. Let me make this voltage less than 0.2. Let me make it 0.1. If I make it 0.1 and run this, now I'm getting a current which is 150 microampere. 150 microampere. Let us see how do I verify this. So let me again go back here. Now when it is in saturation, this is the equation. So what I'll do is it is now 100 exponential minus 6 into 50 into 2 into, of course, VGS was 0.6 minus it's actually 2 times. Let me make it it is 2 0.6 minus 0.4 into 0. How much is this? This is 0.1. Okay, this is 0.1 minus 0.1 whole square, close. You can see you're getting a current of 150 microampere. So this is 150 microampere. So this is 150 microampere, meaning I'm getting a current, because when the MOSFET is in linear region, you need to use this equation. So this equation, you're getting 150 microampere. We are exactly getting the same 150 microampere when we actually simulate it. Now, actually what we did was we actually had this, okay, VGS constant as 0.6 and we varied the value of VDS from, okay, 0.1, then it just made it 1. Okay, now this was the variation. Now can we able to plot a graph where for a given VGS, so VGS is given as 0.6, let me vary VDS from 0 to 1 volt. So this is what we want to do now. I want to plot a graph where VDS is varied from 0 to 1 volt, whereas VGS is kept at 1 volt. I want to know what is my ID, because for smaller, okay, when VGS is 0.6 and VDS is keep on varying, then what is VDS sat now? Because VDS sat, we know that it is VGS minus VTH, that is 0.6 minus 0.4, it is 0.2, meaning till 0 to 0.2 MOSFET will be in linear region. After this it should be saturation. So we know that during saturation the current should be constant. Whereas in this linear region it should be varying with respect to VDS also. So now if you actually plot the graph of ID versus VDS for a given VGS, so it will be constant after 0.2. Before that it will be having a variation, something like this. We say that MOSFET is in saturation region, this is in linear region. There is a transition from linear to saturation where it will be a bit curved. It will not be a straight line. So in order to achieve this, what to do? or how to achieve this. Let me just check it once. Okay, we are there, right? Now, in order to do that, if I do dot op, I will not get it. So I need to vary this voltage from 0 to 1 volt with a constant VGS. So I should use a different simulation command. For that, you should come here in this simulate, go for this edit simulation command. So this dot op was giving different voltage and current for a given values of V1, V2. Now since I want to change this V2 from 0 to 1 volt, I cannot use again dot op, so I should change the simulation command. So go to edit simulation command. Here there is an option called as DC sweep. As you know that sweep is nothing but changing. So what you want to change? I want to change this source V2 value from 0 to 1 volt. So click on this. Now it will ask for name of the first source to sweep. So this is the sweep, this is the voltage source which you want to sweep. Type it as V2. It's not case sensitive, even though if you type small v2 it's fine. The type of sweep is, suppose if you see here, I want to sweep linearly from 0 to 1 volt in steps of 0.1, 0.2. It is a linear sweep. So I will select it as linear. Start value is 0. Stop value is 1 volt with an increment of 0.01. That is be 10 millivolt. This is what I have. See now, earlier this was dot op. You can see this is dot op. The moment I click this, can you see this will become dot DC V2 source varying from 0 to 1 volt with an increment of 0.01 volt. The moment this dot DC comes, this dot op has commented. So this is actually dot op now. Now if I run this, you can see since I'm doing a dot DC, it is sweeping the voltage from 0 to 1 volt. So what is the swept parameter? It's V2. It's VDS on the x-axis. What you should have on the y-axis, because if you can see here, this is what I'm looking at. On x-axis I have VDS, which is the parameter that is swept. On y-axis I should have the current. That is ID. So here I can add the trace parameters. So this is add trace. So what to add now? It's the drain current. Can you see it is ID of M1? If I click on this ID of M1 and then say OK, I'll get this. Can you see here? It's varying like this, it's varying like this, and then it becomes constant here. And you know that when we actually previously did the calculation, we were getting a current of 200 microampere when the MOSFET is in saturation. Can you see, are you not getting the same current here? See here, is it not the same current? Can you see this is, and how to measure the currents here? So I can just do the same thing here, click on this. Can you see this is 200 micro? Of course, if you click on once, you'll get it. Suppose if you click on twice, you'll get one more. This is in saturation region. Let me move one more cursor. Let me just move this cursor and put it at 100 millivolt, because one of the reading was at 100 millivolt. It is this particular reading. Where is that? Because at 100 millivolt VDS, we had a current of 150 microampere. Can you see here? Is this close to 100? Can you see? Is this close to 100? Okay, let me just slightly move this. I'm there. Can you see? It's 100 millivolt. So I'm at 100 millivolt. VGS is 0.6, and what is the current? Current is 150 microampere. And when it is in saturation, that is saturation region, you can have VDS any value beyond 200. If it is 250, 230, 320, 450, 580, whatever the current, you can see this current is almost constant. Of course, not almost, it's 100% constant. So this is how you can able to get the, of course, if you want to see both of them, click on this. You will see the IV characteristics of this MOSFET if VGS is more than 0.4. The moment you make this 0.3, can you see if you make it 0.3 and then run it, can you see the current? Current is in picoamperes, and there is no proper characteristics you're getting. This is a straight line. This doesn't have any meaning here. So this is actually treated as 0. This is picoampere, 10 power minus 12. Suppose if you make it 0.6 now, and you may have a question, sir, how about this 0.1, and then you are making this, whatever value that you have written here will be overwritten by this dot basic. Even if I type it as 100 volt, and if I run, it will not take this 100, it will take this 0 to 1 and then wait. Can you see here? It is still, I have actually run here, actually ran this program. You can see it is still 0 to 1. So this will not affect, this will not affect. Now this is for a particular value of VGS of 0.6. So how about getting one more plot with VGS is equal to 0.8? If I want to get something, okay, sorry, I want to get it like this. So this is at 0.8. If I want to get it at 0.5, it will come like this. This is at 0.5. Can you see I'm having different VGS? Sorry. Can you see I want to plot for different VGS 0.5, 0.6, 0.8, maybe in steps of 100 millivolts of increment in the VGS. You can notice one thing. So this is 0.1, this may be 0.4. After 0.4 it saturates because VDS sat for this is 0.4, VDS sat for this is 0.2, VDS sat for this is 0.1, meaning VGS minus VTH is 0.1, 0.6 minus 0.4 is 0.2, 0.8 minus 0.4 is 0.4, meaning beyond 0.4 it is constant, beyond 0.2 volt it is constant, this is beyond 0.1 it is constant. So that's what we can able to see this uh, family of curves for this MOSFET, that I can do it by not only sweeping this, I should sweep this also. For that, I'll again go for this. I was actually sweeping the source V2. I had to sweep now second, so that is V1 also. I will type it as V1, and it's again a linear sweep. You start from 0.5, you go up to 0.9 in steps of 0.1. Okay, let us start from 0.3 itself. 0.3 itself, because 0.3 is off, 0.3 is off, sorry, 0.4 is also off. 0.5 onwards you're going to have a current. I'll stop it. Okay, now you can see dot DC, you have two sweeps, this V2 as well as V1. You are sweeping this V2, and then for every different values of V1, 0.3 it will sweep, for 0.4 it will sweep, for 0.5 it will sweep. Likewise we'll get 5 to 6 graphs. So let us run this. See now, see this is for different values of VGS, different values of VGS. So what you can do is maybe for a particular, maybe for ID in saturation condition, you can actually find out what is ID for different VGS of 0. Of course, there's no question for finding it for 0.3 and 4, for 0.5, 0.6, 0.7, 0.8, 0.9, with Kp as 200 micro, BTO as 0.4, W by L as 0. Sorry, I think it is 50. What the equation you want to use? You'll be using the equation ID is equal to half Kp W by L VGS minus VTO whole square. So let me quickly find it. So this is 100 exponential minus 6 into, okay, this is 50 multiplied by, this is VGS value, this is VGS. What is VGS minus VTO? Then this will be 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0.5. I just wanted this to find the values of ID. If it is, okay, let me just make it as A square, calculate, and make it 0 0.1. For 0 0.1 it is 50 microampere. For 0 0.2 it is 200 microampere. That's what we actually found out earlier. For 0.3 it is 450 microampere, and for 0. Okay, sorry, I just missed it out. Let me again type it. 100 exponential minus 6 into 50 into, okay, there is a parameter called as alpha a, that's a variable I'm entering, square. Calculate for 0.4 it is 800 micro, and for 0.5 it is 1.25 milli. These are the currents I should get in saturation region. I'll go back here. Let me just put them side by side. Now I should get, of course, except the two readings where the current would be. You can see here. What I'll do is let me just delete this, and again let me add the trace, add trace, drain current. Okay, I have all this. So let me take only one cursor. Can you see the first current is for 0.3, which is in picoampere, which is off. Then you can use the arrow key. You can use the arrow key in your keyboard. You can just use this. Okay, just move to. Okay, now you can see I moved to. This is 50. This is for 0.5, VGS of 0.5, and you can see that is 50 here. This is 50. Fine, this is 50, this is 50. Let me go to the next. You can see this is 200, this is 200. Let me come here, go to VGS of this is 450. Can you see this is 450, 450 micro? Now here you can see this is simulation result, this is our calculation result. Why I want to show both of them side by side is so that you can verify whatever I'm getting in simulation is 100% same as the calculated values. And the next one is just use the arrow key. Can you see here, this is becoming 800. Can you see this 800 micro? And next it is 1.25 milli. This is 1.25 milli. So this is what is the current. And you can observe one thing, the VGS is linearly varied from 0.3 to 0.9, but you can see the variation of the current is not linear, it is quadratic, because we have the expression, even though your VGS changes, okay, linearly, since it is square, since you have VGS minus VTO whole square, the ID changes quadratically. Okay, this is what we intended to show in this simulation, the first simulation of MOSFET. Here, important thing is we should know where to get the component. It is there in this command components, and of course components you have this MOS4, and then you need to define this dot model parameter, which is using this dot op, that is spice directives. And of course I said that I want to show you the syntax. Syntax will be available here. Go to this help, this is here, and you can look for, you can search for MOSFET model dot model. You just say it as dot model. You can see there are so many things, and here you can see this is dot model. You will have, of course, let me just show you MOSFET. You can see this is MOSFET model. Okay, here, see this. This is dot model. We have written NMOS. So here there is one possibility of naming after dot model. Leave a space. You can give even your name. So suppose if your name is Raju, you can give it as Raju NMOS. If your name is Sita, you can give it as Sita NMOS. So what I mean to say is this first need not be NMOS all the time, but this has to be NMOS or PMOS. And what are other parameters? Other parameters can be these many: VTO, KP, gamma, PHI, lambda, WD. So these are the different parameters depending on the level of the MOSFET. The level of MOSFET what we used is very primitive level, where we specified only these two things: zero bias threshold and transconductance parameter, where the default values are this, and the units will not be writing it, but okay, we should know the unit. So this is what the typical dot model parameters are. Okay, we'll see in the next video